Welcome to the Consulting Specifying Engineer webcast, Power for Emergency, Fire, and Life Safety Systems. I'm your moderator, Amara Razgas, with Consulting Specifying Engineer and CFE Media and Technology. For the best virtual experience, here are some tips. If you're having trouble with your slides or the sound, refresh your browser or click the Refresh Media button directly under the presenter's photo. You can control the volume settings by adjusting the volume on your own computer. If you are having technical problems, click on the question mark at the top right corner of your screen to bring up a list of system checks to try before contacting an online technician. If you do need help, type a message into the Ask a Question box and someone will respond in the Answered Questions box. Type questions for the presenters in the Ask a Question box on the left side of your screen. You may ask questions at any time during the presentation, and a Q&A portion will start in about 45 minutes. If you're on Twitter, tweet your questions to us at #CSE Power for Fire Life Safety. Today's webcast is being recorded, and you'll receive an email with a link to the archive in about a week. To download the presentation slides, use the Event Resources on the left side of your screen. For those of you who are interested in receiving one AIA CES-approved learning unit and a Health, Safety, and Welfare unit for this event, you need to pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, use the Learning Unit Exam tab option at the top of your screen. The exam will open in a new browser window, so if you want to take the exam after we're all done, I suggest you open a new tab right now because the link will break when the webcast signs off. The exam will be posted on the Consulting Specifying Engineer website with the archived version of this webcast. In keeping with the American Institute of Architects Continuing Education System Policy, please take some time to read the quality assurance slide. Thank you. Here's a list of the learning objectives for today's webcast. We'll touch on these in today's presentation. Note that any red, underlined text that you see in today's presentation is a hyperlink to a reference or resource to help guide you to more information. Let me now introduce today's speakers. Richard Vedvik is with IMEG Corporation, where he has experience in the healthcare, education, commercial, and government sectors. His electrical engineering experience includes lighting design, power distribution, emergency power systems, and fire alarm systems. He is a member of the Consulting Specifying Engineer Editorial Advisory Board. Rick Rayburn is Executive Director of Electrical Engineering at NV5 and has more than 30 years of experience in development and design of electrical systems. He works in commercial, industrial, government, healthcare, and institutional facilities, and specializes in the casino and hospitality industry. He's a licensed professional engineer in more than 30 states. It's my pleasure to work with two of the most knowledgeable electrical and power experts in the industry. Rich, you're our first presenter. You're live now.
Thank you, Amara, and thank you to everyone that is attending this presentation. We hope you're all staying safe and doing well. Now, we're going to cover power systems for emergency and life safety applications. We've structured this presentation to first discuss how and when emergency power systems are required based on occupancy type, and you'll see we're going to be defining that similar to the International Building Code, or IBC. Next, we'll delve into some specifics about emergency power systems, or abbreviated EPS, and emergency power supply systems, abbreviated EPSS, as defined in NFPA 110. Lastly, we'll discuss some details about mass notification systems, egress components, elevators, and smoke control. Now, building codes may vary based on the project specifics, as well as the list that you see here will vary. Now, for many projects, NFPA 110, which is the standard for emergency and standby power systems, is what we'll use and reference for much of our criteria. Now, of course, if your project's associated with the Department of Defense, you'll reference the Unified Facilities Criteria, or UFC, specifically Section 3-540-01. And of course, we can't leave out the National Electric Code, but that reference deserves its own slide.
Good morning. This is Rick Rayburn in Las Vegas. Thanks, Rich. My task is to discuss mostly in regards to the NFPA 70 or the National Electrical Code. The National Electrical Code identifies two of the criteria for emergency systems and legally required systems, Articles 700 and 701. Specifically, Article 700 will cover and will attempt to cover egress lighting, exit signage, fire pumps, fire detection and alarm systems, emergency egress elevators, safety communication within a building, and industrial processes where severe injury could occur. 701, on the other hand, it will cover elevators in particular. It'll cover ventilation, smoke, and smoke removal systems in buildings that classified requirements of that. Communications in general, heating and air conditioning systems, heating and refrigeration, sewage disposal systems such as lift stations, lighting systems in general, industrial processes where it could create a hazard or hamper a fire rescue operations. The first point of attack would be, from my standpoint, would be an assembly or an entertainment system or building classification, which is identified in the IBC Chapter 3, Section 303. It has Group A, which is for assembly, obviously. But within that group, there's multiple pieces of clarifications. Typically, what it defines is you have to have a gathering or assembly of people that's 1,000 people or more. Now, in some jurisdictions, that number changes, such as in Las Vegas. We modify that to, believe it or not, be only 300 people or more, which is a significant less quantity. So when we have 300 people or more in an assembly occupancy or an assembly, such as a casino or in a convention center or something to that effect, we have to be cognizant of the fact that we have to have emergency life safety systems in place to allow them to safely exit the building in the case of an emergency. It's sometimes difficult because there's different classifications of the IBC with regards to the Group A occupancies. They'll go into specific items within that classification that sometimes crosses over between Group B occupancies, which is business or educational or religious or institutional. There's a number of different classifications, or healthcare. And so you need to be cognizant, work with the architects, work with the owner, understand the building to its fullest extent of the type of occupancies and where they end and where they start within the facility, because some occupancies require special consideration. In the IBC, Chapter 27 addresses the electrical portion of it. It's very short. It's about 3 pages, 2 to 3 pages long, but it specifically talks about standby power, generation power, and emergency power. The first item that I wanted to bring up, because I'm most familiar with it, is casinos. I've highlighted some of the items that are typically seen for casinos as far as, I'll say, generator power, because one of the concerns that I always have is the different players that are involved in design of facilities, whether it be a casino or an educational facility, is everybody looks at the word emergency differently. And for us, emergency power for this type of facility is determined by Article 700 in the National Electrical Code, in conjunction with the other codes that Rich had mentioned, such as NFPA 110. Many people, when they hear the word emergency, they think that their equipment needs to be on that system. The reality is we're only allowed to have certain things, as mentioned before, on that system by code, because that system is an independent independently wired system within the building. Egress lighting is one of them. So the IBC defines egress lighting in the case of emergency to be 1 foot candle average measured at the path of egress out of the building. Now, as an electrical engineer, it's difficult for me to define the paths of egress many times, specifically, for instance, in this casino. And it's up to the architects and interior designers and other professionals in the design of this building that's going to be the person that's ultimately responsible for defining egress pathways in a building. This one is pretty easy to see. You can see a carpet path amongst the slots and the table games. That's pretty much an egress path. However, if I'm sitting at one of those slot machines, my path might be different. So while that's a minimum requirement, 1 foot candle average, doesn't mean it has to be followed as far as the minimum you apply. You may decide to put 10 foot candles. You have to think about the people that are using these machines also. A lot of them are elderly and don't have good eyesight. It's harder for them to get around. So take those in consideration. Exit signage is another item that has to be put on emergency lighting. In this photo here, you really don't see any exit signage in here, do you? It has to be within 100 feet of where you're standing in all cases. There is, it's just this picture didn't show it. Slot power. Slot power is not an emergency power system or a 701 system, legally required. It is optional standby, which is Article 702 in the NEC. Smoke removal system could be required in this building. It may not be required, and that's where the code officials and the architect all work together to define whether it's a requirement for this particular occupancy. Elevators, if this is a multi-story facility, may be required to have emergency 701 power brought to them. The items that aren't on this list are fire alarm system, as I mentioned before, and if a fire pump is required. Fire pumps may be required because of the flow requirements. I threw this slide in here because I ran into this project, which was actually part of a multi-use facility here in Las Vegas. It happened to be an equestrian center that was put into place for a casino operations that also had exhibition halls, meeting rooms, theaters, had pretty much every type of occupancy you can think of with the exception of possibly religious applications. But the reason I put this in there was, as a specifying engineer, this particular equestrian center had over 1,000 horse facilities to store horses in here, or to keep horses during an event. So when I looked at this, I thought, well, this is really no different than that casino in that regard as far as being able to get people out of this area. Typically, if there's a horse in there, there's usually a horse handler in that space. So if I have 1,000 stalls in there, there's a very good possibility I'm going to have over 1,000 people in this building. So you can see an exit sign here. There's one at the end of that pathway, and that's obviously an egress path, needing 1 foot candle in the path. How do I calculate the foot candles in that path? If the floor is dark, I have to take those things into consideration because your reflectivity in the space also comes into play for maintaining that 1 foot candle average. My professional opinion is that you should always overlight a space for egress lighting. This particular area had elevators, it had fire alarm, it had smoke removal system. It had pretty much everything involved. I should state back, the smoke removal system was more or less for vapor removal because of the smells that were created in this space. I threw this slide in there again. Once again, this is part of a multi-assembly property. A lot of the local casinos in Las Vegas will have bowling alleys tied with them. Now, the first impression is to say, well, a bowling alley, how can I have very many people in there? Especially if you look at it from the IBC standpoint, probably never going to reach 1,000 people within this space. However, in Las Vegas, because we have an assembly occupancy of 300 or less, or 300 or more, I'm sorry, the possibility could occur here. If I have 4 people bowling on each lane and there's 72 lanes, there's already 280 persons in this space that I have to plan for to get out of that building safely. I obviously don't exit them across the bowling lane, so that's not of major concern. But a bowling alley is also needs to be considered, especially when it's applied for the application you're dealing with. How do I get those people out of that building safely? Where is my exit signage going? Is it visible? Is there elevators? Is there a fire rescue elevator planned for this space? Typically not for this type of application, but maybe. A fire alarm? Usually a fire alarm system is involved in this. On this topic of education, now we get into an education facility, you'll also apply IBC Chapter 3 in Section 305, which is a Group E classification. The Group E has 6 or more for education purposes through grade 12. If you have 6 or more people for education purposes through grade 12, it classifies in the Group E classification. The IBC, again, requires 300 people or more in that facility to be deemed an assembly or an education facility. Southern Nevada reduces that to 250. Not a big change. We have to worry about the same type of things, but now we're worrying about it for children primarily. And so again, you have to think about, how do I get people out? What's their eyesight? What's the needs for the spaces? Where do I apply emergency lighting? Again, egress lighting, do I do it in the classroom itself? Do I provide it obviously in the corridors as I'm leaving that facility, in the exit signage? Do I make sure that children know where to look? And a lot of that's procedural after the building's built, but if you haven't applied it and put it in the proper locations and thought about it, in particular, one of my items that I try to do is make sure that I have a light in the classroom that would be on in the case of a power outage. Doesn't mean it's on during the normal use, but in a power outage it would come on to let the teacher and the students be able to exit that room safely. And with that, I'm going to turn this over to Rich.
Thanks, Rick. If we have a healthcare application, then NFPA 99 and or the FGI guidelines will be a necessary reference. And in 517.30 in the NEC, we have a requirement for 2 independent sources of power. Now, since the adoption of 2012 NFPA 99 by the CMS and Joint Commission, the facility should perform a risk assessment that determines how the space will be used, who will access the area, if injury is possible with a system failure, and the severity of the injury. This will drive the decision of the category type. NEC 517 also defines categories of the patient care space as 1, 2, 3, or 4. A simple way to think about it is like this. If people could die if the system fails, it's category 1. If they could be severely injured, then it's category 2. If they're made uncomfortable, it's 3, and if it's just an inconvenience, then it's category 4. So regardless of what your occupancy type is, if you have a category 1 or 2 space in your building, as defined by 517 for patient care, it'll have to have emergency standby power. You'll see B occupancy surgery centers that you'll assume it's a B occupancy, but because it contains category 1 and 2 spaces, it has the requirement for emergency power. Now, if your emergency source is a generator set, you will have environmental concerns that can be exacerbated with healthcare applications. Many of the guidelines for healthcare and patient care areas have noise limits associated with them. FGI, LEED, WELL certification, ASHRAE, etc., all have recommended or required noise criteria. Additionally, you may have state or municipal noise sources and property line requirements. Here in Illinois, for example, Title 35 of the Illinois Administrative Code is highly restrictive, and standby power systems are not exempt. The physical location of the generator will inevitably drive the noise attenuation requirements for that genset and maybe even the building facade. Another factor that we need to consider, regardless of occupancy type, but of specific interest to healthcare, is the proximity of the generator exhaust to the building HVAC intakes. Exhaust smells are not pleasant, and if those smells come into an operating room or patient room, you can expect to have a very upset client. Many of the times, we're making changes to emergency systems. and outages are likely to occur. Now, in this photo, you're seeing a project in which we had to upgrade the emergency paralleling gear in order to increase its capacity to a healthcare facility. This is a huge undertaking, and this means throughout the duration of the upgrade, the emergency power system was not going to be made available through traditional methods. In the photo, you can see cables that are hanging down from the ceiling. Those are temporary locomotive cables that run outside to a temporary generator. We had to coordinate very carefully with the Department of Public Health in order to get approval for how we were going to actually execute this switchover. This meant taking the hospital facility on emergency standby, coordinating throughout every single department within the hospital campus of all the different departments and all the department managers, verifying that batteries worked, what were we going to do if we lost normal power, communicating with utility. It's a very detailed and important item to consider. And throughout many of your projects when you're remodeling, always take into consideration that if you want somebody to make a connection to a bus, they're going to have to shut it down. And if that means locking out the generators, then you don't have emergency power. That means you no longer meet the requirements of 517. So always take that into consideration as a special impact to healthcare, but something that also impacts the occupancy of other types. Now, in the 2018 edition of the FGI guidelines for the design and construction of residential healthcare or support facilities, you'll find essential electrical system requirements for ventilator-dependent residents. The process defined for risk assessment under NFPA 99 applies to these occupancies as well. So designers may also reference the U.S. Department of Veteran Affairs website for design criteria. The Technical Information Library, also called TIL, is a very useful resource that has been honed over the decades, and it has fairly detailed information on how to design a variety of facilities, including long-term care. Mental health facilities will follow the same process for determining risk categories, and thus the need for a central electrical system. IBC Section 403.4. This defines systems that are required to be on a standby power source. Now, the primary focus for a building of this type is centered on egress. If elevators are to be placed on emergency power, the designers will need to decide if they will also be used for occupant evacuation by the fire department. Now, we'll discuss specifics on elevators, egress, and smoke control later, but it's those types of systems that result in a high-rise application needing to have emergency power. Another requirement for high-rise is the need for a fire command center. Now, this is where the fire department will take control over all the building systems, such as the elevators and the HVAC and emergency power. This is typically a room that's located at the fire attack entrance. You coordinate all of this with your fire department ahead of time. Shown here is a project currently undergoing a full historic renovation. Because it's located in the northern climate in Illinois, we're also putting building heating systems on emergency power on select floors to prevent freezing and burst pipes. Now, as Rick mentioned previously, what you can put on each branch is going to be defined within sections of code. So we'd be in an optional standby in this sort of application. Now, the emergency feeders in a high-rise application, they will be subject to NEC 700.10d. This section lists options for providing fire protection for emergency feeders. The idea here, of course, is that if I have a fire in one part of the building, I don't want that fire to take out my emergency feeders that serve the rest of the building or another part of the building. Now, if you're curious a little bit about what fire systems you can use, UL 2196 is the standard for the fire test for circuit integrity of fire-resistive power cables. It's very long, and it uses a couple acronyms that don't seem to match up to the definitions. For example, fire-resistive cables are FHJR, and they're intended as the installation of specified individual electric circuit integrity systems, which is abbreviated FHIT. Now, normally in our industry, abbreviations are actually, they match the words that are associated with them. Just understand that here they do not. But what they're talking about is, say, mineral insulated cable or special fire-resistant metal clad cable. Maybe it'd be RHW2 in a RTRC or phenolic resin conduit. And you may even have like power-limited fire alarm cable that'd be located in EMT. So now we get to the types of emergency power systems, or as NFPA 110 calls them, EPS. Now, we do have options. While we typically see generator sets being used, and a lot of our examples are generator sets, code does allow for fuel cells or batteries or DC microgrids. Now, regardless of the makeup, code defines the requirements for time transfer, run duration, and we'll discuss a little bit about that later. The most popular question is the use of natural gas for emergency standby. The issue with natural gas is the lack of on-site storage. A letter from the gas company stating the reliability of their system might be sufficient for an AHJ to approve the use of natural gas. Designers will refer back to my previous discussion on risk assessment, and they can apply that logic to their specific project, regardless of building occupancy. If the failure of a natural gas supply only results in the inconvenience or discomfort of the occupants, then using natural gas for a generator could be an excellent option. Now, we can't talk about natural gas versus diesel without mentioning the EPA. Tier 4 is the most stringent requirement for generator sets, whether it's diesel or natural gas, and the requirements are different for each one of those. Now, while an entire presentation can be given on Tier 4, the primary takeaway is that the more popular Tier 2 classification cannot be used for financial gain for peak shaving contracts with a local utility. So that's one of the common questions I get from owners. Hey, I got this gen set. I can save 50 grand a year if I just peak shave. Can I do it? And the answer is, if it's Tier 2, no. The other question I see quite often is, should we use medium voltage generators? I personally, if I have a large hospital campus or a large campus in general, and I need to distribute from a central utility plant, I'll strongly consider like a 5 kV generator set, which means you're going to have unit substations placed in each one of your buildings for emergency power distribution. And we'll typically see these as parallel gear. The photo on the left is 5 kV parallel gear. Now, if I want to do full campus backup, then I might be going 15 kV, and in which case I'm either going to parallel or just simply replace the utility company entirely. That's the generator on the left. Now, if you're going to determine how big to make your campus backup gen set, I'm listing in there IEEE standard 602-2007, because there's a table in there that actually lists the service entrance demand for 37 different hospitals throughout the country based on the square footage, number of beds, etc. So it's a really useful reference for designers wondering, how big should I make these gen sets if I'm going to be doing medium voltage applications? Now, managing the size of a generator is done through the use of load steps. This is done with transfer switches and managing the load on each transfer switch. Designers will determine the order that each transfer switch is applied to the system as they come online. Software is used to calculate the resulting voltage dip and frequency dip associated with each load step, and that's what you can see here in these images. You can see step 1, step 2, step 3, and the amount of load on each of them. Now, you can sometimes reduce your generator size by increasing your number of transfer switches and thus reducing the step load that's going to be seen. You're going to coordinate that with approved generator vendors and the softwares to make those calculations. Another handy reference I listed is another table in IEEE standard 602, and that is emergency generator loading measurements for 74 locations across the country. And they break it out by watts per square foot and the location. Now, an EPSS, or Emergency Power Supply System, as defined in NFPA 110, consists of distribution electrical gear and transfer switch equipment. And NFPA says that this equipment has to be physically separated from normal service. And we'll get into that here in another slide. But you're going to see levels and classes and types. So level 1 or 2 is very similar to our discussion on loss of life. If somebody could die with the loss of utility power or a system, then level 1 is going to be your selection. It's the most stringent. The type is how long power can be out between the transition from normal utility to the EPSS. So U is uninterruptible, then you have 10 seconds, 60 seconds, or 120 seconds. And lastly, you have manual transfer, meaning it take as long as you want. Now, which one you're going to fall under? Again, you're going to be doing your risk assessment and following both the NEC and NFPA. Now, the class is the runtime in hours. So how long does it have to run? In healthcare applications and seismic zones type X might even be 96 hours. So you're going to coordinate this with your AHJ to determine what you actually have to do for each one of your EPSS selections. Now, we have to talk about 3-pole versus 4-pole transfer switches. And that's going to be based on whether or not your system is separately derived. Simply put, what we're looking at here is the neutral current that's normally returning back to the source on the utility side, for example. If you have a 3-pole switch with a solid neutral, that neutral current is going to split and go into 2 different directions. It's going to try and go back to the emergency source and the normal source. And if there's any bonding on the emergency side between neutral and ground, then you're going to have return neutral current on your grounding system, which can cause nuisance trips of any of your ground fault breakers on your main distribution. The easiest way to solve that problem is with 4-pole switches and separately derived generators and normals. Ideally, that's exactly what you'd want to do for most applications, but you're going to run into an issue when you go to upgrade existing facilities. Now, for closed versus open, we want to take into consideration the disruption that we're going to see in an open transition. And we're talking from normal to emergency under test or emergency back to normal when utilities returned. That slight blip, that can cause failures of building automation system controllers. It can also cause computers to drop out. So you're going to coordinate whether you want open, closed, or maybe even delayed transition for each one of your applications. I previously mentioned that the EPSS equipment requires a separate room. The definition of normal service equipment could be considered to be limited to Article 230. But we also want to understand that the only intent of this is that if I had a catastrophic failure of my normal source, I don't want that to damage my EPSS. So if I have a unit substation, for example, sitting inside an electrical room, while that might not be fed by the utility, but a campus-owned distribution system, that's still our normal service equipment for the intents and purposes of this code section. So I want to keep my EPSS separate from normal service, high amperage. I'm thinking about my risk assessment. I'm always saying, what if that fails catastrophically? Can anybody die? And in a healthcare application, the answer is yes. So we're going to take that into consideration. If we're replacing transfer switches or equipment, we have this tendency to want to put them back in the same location they were. That makes sense if it's a legal location, but if your building's more than 30, 40 years old, it's very likely everything's combined into one space. I want designers to pay very careful attention to this and make sure that when you're replacing EPSS equipment, it's going into a legal location and not just its previous location. And that also means coordinating with the foreign systems that are likely to exist, such as ductwork and plumbing. Now, the branches that we have for NEC 517, of course, are going to be life safety, critical, and equipment. And NEC has informational notes and sections that actually explain what is supposed to be on each one of those. Now, some of that stuff moves around between critical and equipment. You have some options, but you're going to be following those pretty defined limitations within NEC for what you can place on each one of those branches. We'll also talk a little bit later about reliability of these systems and what that means toward separation of each one of these branches.
Thanks, Rich. I'll take it. So this is in discussion on the application APS branch circuits as it applies to NEC 700. I think one of the misconceptions a lot of times is that we see receptacles placed on emergency life safety circuitry. The reality is this: as a designer, I want to guarantee, no matter what, that emergency distribution system, all the way down to the branch circuit connection to the equipment that's operating, is going to operate properly. Nowadays, we get into branch circuit requirements with SPDs all the way through the distribution system of Article 700 and 701 requirements. But back to that receptacle, in the past, there was a lot of designers that would put receptacles because somebody said, hey, I need to make sure that my equipment operates in an outage. So they would put receptacles on emergency power. The reality is this: we as engineers don't know what people are going to plug into that. They might put a space heater, for instance, which may, because of lack of selective coordination, instead of tripping the branch circuit because of a failure of that piece of equipment, it may take out the main breaker upstream. So there's several items there that are at fault. Number one, no selective coordination or little selective coordination. The code requires complete selective coordination on an Article 700 system, and we'll talk more about that later. But in all cases, try to avoid putting receptacles on emergency power, Article 700. The other item I wanted to discuss was in branch circuits being contained in a raceway with other systems. You cannot put emergency life safety under Article 700 in conduit or raceways or wireways within any other circuitry that's in the building. So if it's Article 701, can't put it in it. If it's standard power, can't put it in it. UPS power, unless that UPS power is deemed for life safety, can't be put in it. Some of the other items that I wanted to bring up on this was identification. The code specifically says that if you do provide a receptacle for some reason on Article 700 system, it needs to be a specific color. It needs to be identifiable. The same with the labeling of your equipment. It needs to be identifiable very readily. A lot we use, for instance, red placards on the equipment with white lettering, so it's easily seen. All junction boxes, all gutters, even conduits that are exposed need to be labeled, need to be labeled as to the content that's in it, so you can easily identify where that emergency system is routed and what's in it. Ratings and survivability. I'm going to pass this over to Rich for a few minutes.
Yep, so we discussed 2-hour rated cable assemblies in a high-rise application, and they're going to apply here as well. We want to note that NEC 517.31, it requires that life safety and critical branch wiring be kept separate from other branches, just as Rick had previously mentioned. And keep in mind, this applies to panels, panel boards, pull boxes, junction boxes, lighting control, contactors, etc., unless a listed barrier system is provided to provide that separation. In addition, 517.30 Section C says you should have physical separation of your feeder routing to minimize possible simultaneous interruption. We keep coming back to this. You shouldn't have a failure of a less emergency system, a normal or an equipment branch system, taking out your life safety or critical. And I'll let Rick talk a little bit more about 700.
Thanks. So in 700, 710D, there's 4 specific items, and I'm going to concentrate primarily on equipment and feeders. Specifically, the code says that spaces, as long as you're allowed to run feeders and put equipment in spaces that are within a sprinkler's capability. So if you have sprinklers in a space and that equipment and feeder are directly under the spray of that sprinkler, it's okay. You can put it in that location. However, if you're in a building that has sprinklers and you're routing that feeder above the ceiling where there's no sprinklers, that's not in compliance. So again, there's several different items such as 2 inches of concrete for the feeders, a listed fire rate assembly. We've touched upon a lot of this stuff. The equipment can be in a sprinkler space or in a 2-hour rated room. A room that's 2-hour rated. Now, does that equipment need to be completely separate from normal equipment? If I have a standard panel board in a room and an emergency panel board in a room with upstream transfer switch and so forth in the system, I'm allowed to be in the same room. The transfer switch is a different item along with the generators. Those are separate items. But when you get down to the panel board distribution, if it's within a sprinklered room, you're allowed to put it in there. Redundancy. So Article 700 requires the system to incorporate now a temporary generator or temporary connection for maintenance of your emergency generator. What that means is if you have a simple system, and we'll just say that you have a generator that's connected to a single transfer switch that's Article 700 required, and you need to provide a backup generator for that for when this thing is being maintenance so that the building can still be occupied under normal conditions. So, there's equipment that's made now, transfer switches that have lugs to plug in a separate generator. There's switchboards that are made to have a separate cam-locked connection for a temporary generator be brought in. You want to make sure that you've covered that because generators need maintenance. There's no doubt about it, and many times over a period of 20 years, they may have to be totally rebuilt over a several-day period. You need to have the capability for easily connecting up equipment or generators. The other thing is, in redundancies in the system, in as much as this is my life safety system in the building, what I've seen a lot of is designs that incorporate what we call wraparounds. So if I have an emergency generator distribution system and for some reason or another, I need to maintain a switch that's in that system. Well, I don't want to take that system down completely. So I might have the capability of wrapping into a 701 system for a short period of time or into another 700 system that brings me power for a temporary period of time within my distribution system to keep it active. Campus power distribution was touched upon a little bit ago by Rich. Again, a distribution system, if you can think of it this way, it's an extension of the generator. It's my emergency power loop on a property. And when I say campus system, I'm thinking of a university or several building occupancy location where I've got several buildings strewed around a campus. So if I put a normal distribution loop, I may back up that normal distribution loop, but guess what? That power that's feeding off of that loop may or may not be deemed as 700, depending on the authority of jurisdiction applicable. I may have to have a separate distribution feed from my generator system out to the buildings, each one of those buildings having a separate transfer switch to be fed off their normal power, which is a separate feed distribution. To pick it up. And I can feed 700, 701, 702 off of that, more or less tapping the feeders. Selective coordination, I touched upon that. It's been now conformed to be in both in 700 and 701 under point 32 in the NEC. And selective coordination, for those of you who don't know, means that the closest device to a fault in my system is going to open first. I do not want anything upstream to open. So if I have a branch circuit that has a fault to ground, somebody faults it to ground, I want that closest breaker to open or closest fuse switch to open, not the main and the distribution board. So it's a requirement of code. It has to be down to the 0 period of time for 700s and 701 systems. And I'll turn this over to Rich.
Thanks. So one of the things that's changed throughout the decades is the topology of our design. The way that we design systems for selective coordination and managing arc flash and the SCCR has changed the way that we're doing things. We used to have a lot of sub-distribution panels. We're not doing that anymore. Now we're trying to make sure that we comply with selective coordination, but that's also having a side effect on the amount of arc flash energy that we're going to have available. Now, when we're doing these calculations, I do a comical example here. This is a sticker on a piece of gear, and the result of this calculation was because they didn't take into consideration primary fusing on a large transformer. So obviously, a flash boundary of 1,556 feet isn't necessarily very useful, but we want to take that into consideration when we're doing these calcs. Remember that it's still software, and whatever information we put in is going to determine what kind of information that we get out. NEC also has a new requirement for start conductors and them being supervised. Essentially, what designers need to do, you're used to pulling 2 wires back to the generator, keeping them separate. Now you're going to add a third. That third wire is to basically give the gear the ability to monitor voltage at the start conductors. Your ATSs, they're going to have switch position and source availability. Besides testing, you want extra cables to provide that data information to your paralleling gear. You're going to have, of course, either your load shed or load inhibit. That inhibit will be used with paralleling gear to get multiple generators to control, remember those load steps that we talked about previously? Those load steps will be managed through those inhibit and load shed signals. And lastly, your annunciator locations are going to vary throughout the facility. You're going to coordinate that with your facility. Now, egress within our building is important. We have to take into consideration our elevator lobbies, and if our elevators are going to be used for evacuation during a fire, we have to, A, have an enclosed lobby for them as required within NFPA 101, and additionally, we will remove the sprinkler shunt trip controls. Now, that's important for designers and engineers to understand. We're so used to putting shunt trip on elevators, but if we're going to use them for fire rescue, we can't do that. All these egress components will come into play through NFPA 101 as well as elevator code. Now, Rick's going to go a little bit more in detail about elevators for us.
Thanks, Rich. Elevators, real briefly, have come a long way in our times. And it's important to pay attention to the elevators that are going into your building because some of them are used for firemen's egress purposes and for service of the building. The most important thing that I've come across in the recent past is, again, that a lot of times the elevator inspectors don't understand the difference between emergency power and legally required standby power. Legally required standby power is the typical power source you're going to use for your elevators in your building. However, it doesn't limit you to say you can't use emergency power. Specifically, when they're used for firemen's egress purposes or firemen's assistance to evacuate the building, the lighting in the core of that particular elevator needs to be complete throughout. So wherever that cab stops, there'll be 1 foot candle on the top of that cab because that may be the path of egress to get people out of the building. Again, this is just another photo from one of the projects showing a multi-elevator room with VFD driven and an individual one. Smoke control systems. Smoke control systems are going to be defined by obviously the size and type of the building and the occupancy. IBC 90911 addresses it. They are connected via NEC 701, and they need to be on within 60 seconds. There has to be enough fuel for 2 hours of operation, and they need to be in a 2-hour fire-rated room per NEC 701 equipment. There is the stipulation of a sprinklered application for those rooms. The wiring for those systems, albeit they can't be cables, they have to be in raceways. And with regard to smoke control systems, this is just a clip out of what we utilize for when we're doing design work in our facilities. It lists out legally required equipment for 701. Within that, you'll see items that are smoke control related, such as, believe it or not, sliding doors for rated openings could be deemed as a smoke control item. Tower ventilation exhaust fans, sewage ejectors are not smoke control, but you need to take those under 701. Smoke control equipment, tower smoke exhaust fans, stair pressurization fans, they're all utilized to make sure that the firemen can utilize that typically for cleanup of the building and making sure that everybody's out. And with that, I'm going to turn this over and grab a sandwich. No, I'll turn this over back to Amara.
Okay, thank you so much, Rich and Rick. That was fantastic. As a reminder, you can earn 1 AIA CES approved learning unit and a health, safety, and welfare unit for this event, and you do need to pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, use the Learning Unit Exam tab option at the top of your screen. You can also download the slides. We do want to let you know about another opportunity. So while you're looking for more continuing education, in addition to this AIA CES approved event, you can attend a CFE EDU continuing education session sandwiched in between all of your other virtual meetings. Once you download the slides for this presentation, you'll have the direct link to more continuing education. Rich and Rick will now answer questions on this topic. Please type your questions in the Ask a Question box on your screen. And if you remember who is speaking, type the presenter's name before your question so that I know who should answer it. We'll get to as many questions as time allows today. Answers that we don't get to will be posted online at www.cscmag.com as an article in about a week. All right, gentlemen, we are going to take questions now. Rick, the first question goes to you. please explain the difference between emergency power and standby power?
Thank you. Actually, the term standby power is many times used in the terms of generators themselves. So a generator can be called a standby generator. However, that shouldn't be misconstrued with emergency power or standby. Emergency is, again, associated with the life and safety of the occupants of that building to get them out of the building safely. Standby power, legally required standby power, and there's a couple different definitions there. There's also standby power that's utilized for whatever the owner wants it for. So there's really three classifications of systems that we utilize in the code. 700, which is emergency for life and safety of the occupancies. Legally required standby power, which is utilized for those equipment to help a fireman clean up the building. And then optional standby power, which would be for the owner's request, such as possibly a refrigeration unit or slot machine power, the power that serves slot machines. Hopefully that explains it.
Yeah, fantastic. Thank you very much. Rich, this next question is for you. Do assisted living facilities have special emergency power or generator requirements? Can you talk about that, please?
Sure. In the assisted living, we mentioned that anything that's ventilator-based is listed within NFPA 99 and FGI guidelines. And again, that always comes back to the risk assessment. And that's the main takeaway that I'd like a lot of the participants to have, is that when you're looking and wondering, do I need emergency power and what branch does it fall on, you're going to ask yourself, which category does this space fall in? Which level does it fall under? Is it level 1 or level 2? Can anybody die? Can they be injured? Are they just going to be inconvenienced? So when you're looking at long-term care, the answer is exactly, the process is the same, I should say. If they're on life support equipment or on anything that if they lost that equipment, they could risk serious injury or death, then yes, you're going to have emergency power available for that.
All right, got it. Thank you. If you have additional questions for our presenters today, you can ask a question in the Ask a Question box on your screen. If there is something that we didn't get a chance to address during the live presentation here, you may download the slides to review it. That may help you answer any of the questions that are in the exam for the AIA CES Learning Unit. All right, let's see here. Rick, you have the next question. When are elevators required to be on generators? Rick, can you give us a little bit more information on that?
Sure, I'll do my best. The requirement for elevators to be on generators is really up to the AHJ and the codes that you're applying to and the use of the elevator. Let's say you have a 2-story building and an elevator to transfer between those 2 floors. If that elevator is being utilized as a fire service elevator or deemed by the authority having jurisdiction to be needed for that purpose, it would need to be on backup power. We've been using the term generator power. It doesn't have to be a generator. As Rich pointed out, there's other sources of emergency power that could be utilized or in this case, legally required standby power that could be utilized to take care of that. There's even some jurisdictions that classify the power from the utility as being available all the time, and they'll allow you to utilize a second source from a utility as your backup power. I very rarely, if ever, have seen that, but that is in the code. So back to the elevators, typically high-rise applications, wherever the authority having jurisdiction, along with the architect and code authorities that are on your particular project, will define that the elevator needs to be on generator power or backup power, and is typically is legally required standby system that would feed it.
That's good, Rick. And one of the things I'll add there too is as you're looking at all of these emergency power applications, if you have other systems besides mass notification systems or egress systems, smoke control, et cetera, you're going to constantly come back to that risk assessment and saying, can somebody die if we lose this? That's going to tell you whether it's going to be emergency or life safety. or critical, or optional standby, or equipment, or legally required. So remember that those branches have times associated with them, and if it doesn't have to come on within 10 seconds, that probably means we're not worried about the loss of life. This is more of a convenience or a ancillary system.
Yeah, good information. Thanks, Rich. And again, if there was something that you missed in the presentation, you can download the slides that will give you additional information. You can also ask a question of one of our presenters by tapping on the Ask a Question box. And of course, you can take the Learning Unit exam by clicking on the Learning Unit exam tab. Okay, let's see here. Rich, I'm going to send this next question over to you. And this is referring directly back to one of your slides. Does it mean that a 4-pole transfer switch is for Y transformer output, while a 3-pole transfer switch is for the delta transformer output?
See, that's an excellent question. And I could do an entire hour just talking about 3-pole versus 4-pole and applications, and we could get into the details on that. But what you're always going to take in consideration, we see a lot of 3-pole switches with solid neutrals in Y configurations. Now, if there isn't a neutral being used, for example, it's motor control center, it's 3-phase motors only, and you don't have a neutral, then having a 3-pole without a neutral load on there is fine. You're always going to think about, do I have separately derived systems or not on the generator as well as the utility, and what's that pathway back for the neutral current? Because remember, our neutral is giving us a pathway back to our normal source. I've done generator installations that were a high impedance neutral, so they were a Y 480 volt generator, but instead of taking the neutral conductor to the paralleling gear, we would run that through a high impedance resistor or a neutral grounding resistor. We do that at medium voltage occasionally too, where we have a Y output, but we don't necessarily need a neutral, and we're going to be running it to transformer primaries anyway. So it can get very confusing, I would say, but it's also it's kind of fascinating. I think it's just a wonderful topic to think about. And if it's a brand new building, then you make the decision and you move forward with it. It's when you get into a lot of existing buildings where you're adding on the systems. Don't just put in 4-pole switches with switch neutrals when you already have a whole campus full of 3-poles. You might have some really weird problems with your ground fault sensors.
All right, yeah, good. Lots of information there, not enough time for sure. Rick, I'm going to send this next question over to you. Rick, if you have an office building that is on backup generator in its entirety, do you still need emergency lighting?
Good question. This is, kind of a loaded question too, because first off, you got to define the building. If I have an office building that's similar to the one I'm sitting in right now, which is maybe 10,000 square feet, and the client, upon design purposes, says, I want to have my entire building on, I never want it to go down. I want it to be on generator power all the time. So the engineer designed a generator to back up the entire building. The problem with it being classified as emergency power is the fact that it's not a separate wiring system that's self-contained and deemed to comply with all the requirements of Article 700. So the generator is not acting as an emergency generator. It's acting as a standby generator for optional power requirements. So the lighting within the building for egress purposes, yes, you would have to provide other means to provide backup, such as individual battery units or an inverter system within the building that would back that up. And that wiring would all have to be separate if it's wired. If it's individual lights that have batteries built into them, then that will take care of your needs. Just depends on the size of your building and whether or not you want to have that separate transfer switch. And again, that falls back to the assembly occupancy requirements.
All right, here we go. Last question for you, Rich. This is the last one we have time for. If your ATSs are 3 poles, is there a way to avoid nuisance ground fault sensor trips required for the legally required loads?
Yes, so this comes back to, if you have 3-pole switches, then you do not have a separately derived system on your generator side. So your emergency power side's not separately derived. That means you're not going to do your neutral ground bonding there. Instead, you're going to do it back at the main source. You're going to have to take into consideration what your ground fault sensor trips are going to be set at. And unfortunately, in most applications, you're going to find that they're going to be higher than you would like them to be. However, we also have ground fault coordination. So as you're taking a look at your coordination settings, you're going to be doing that for ground fault as well. One last question was whether or not flywheels are considered emergency sources in the U.S. For this, consider back to NFPA 110. And what is a flywheel source? Does it comply with run times? Remember, your types and your classes are going to tell you it's great for an interruptible power supply source, but is it going to last 15 minutes, an hour, 4 hours, 48 hours? Whether or not it's legal is going to depend on how long it can run. And in most cases, flywheels are really just to ride through while the generators are getting started.
Okay, cool. Great information. And now that the technical portion of this webcast is done, I'd like to close by thanking our astounding speakers, Rich Vedvik and Rick Rayburn, for sharing their wide-ranging knowledge and understanding of power for emergency systems. And now we want to hear from you, audience. A short survey will pop up on your screen as soon as the webcast ends. Please take a few seconds to complete it. We do want to hear from you because we use this information to improve future education. Finally, on behalf of Consulting Specifying Engineer and CFE Media and Technology, thanks for attending this webcast. This is the end of today's event. Thank you for joining us, and we'll see you again soon. Goodbye.